Good evening everyone and welcome to the 12th live session for the course Introductory course in Real Analysis. So today's session would be mainly focusing on integrability of functions. Okay, so in particular Riemann integrability. Okay, so let's begin with this problem. So this is the function. Okay, so fx is x when x is a rational number, otherwise it's 0. Okay, so in this problem you have to find what will be the upper integral and the lower integral, or upper Darboux sum or lower Darboux sum. Okay, and then we'll see that whether that matches or not, to conclude whether this function is Riemann integrable or not. Okay, so let's start with this. So one thing is very immediate, okay, that the lower sum, okay, so maybe I should write. So this is the function. So fx is equal to x when x belong to 0 1 intersection q, and it's 0 when x belong to 0 1 intersection q complement. Okay, so one thing is clear, that suppose we take any partition. So let P be any partition for the interval 0 1. Okay, then so let's say I'm denoting this as, so P is equal to, so 0 is x0 x1 and dot 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 till xn, and this is equal to 1. Okay, so this is any partition we are taking. Now if I want to calculate what is UFP, okay, so I hope you remember the definition. So this is defined in the following way. So you take the supremum of the function, okay, on the interval xi to xi plus 1, okay, of f. So take the supremum and then take the length of this interval xi plus 1 minus xi, and I will vary from 0 to n minus 1. Okay, so basically on each of the interval you have to take the supremum and then multiply it with the length of the interval. Okay, so this is how you define this upper sum. So now you can just simply, you can see. Okay, so let's not talk about first this u, let's talk about this m first, or the lower sum. Okay, so we'll talk about the infimum. Okay, now you can see here in this function, whatever interval you choose, you know that there will be a rational number inside this interval, correct? And at that irrational point the function will be taking the value 0. So the infimum of the function in any of the subinterval will be 0, right? So this whole summation will turn out to be 0. Okay, now if you calculate this L of f, which is the supremum of such LFP, right, where P is any partition, so there P denotes any partition of the interval 0 1. Okay, now we take the supremum, so that will again be turned out to be 0, correct? So that is nothing but this integral 0 1, the lower one of the function f, is becoming 0. Okay, so this is about the lower sum or lower integral. So let's talk about, to get what will be the upper integral. Okay, so now you already know that for the upper one you just have to replace this infimum by supremum, and here you have to replace supremum by infimum. Okay, but there is another way of calculating it. So what we'll do now, so we'll consider particular kind of partition. Okay, so I'm denoting, let P, or let's say, okay, Pn. Okay, so this is one partition that I'm defining. So this is nothing but 0. Okay, so this is your x0, and then the next one, now let me write it in this way directly. So 0, and then the next one would be 1 by n. Sorry, I should not write it in this way, maybe I should. So basically I'll just draw it first. So I'm choosing some natural number, okay, 0 1. So let me write it in this way. So let n belonging to natural number. Okay, so what we are doing, we are dividing this interval in equal part. So maybe I'll write, so this is the length, let's say 1 by n. Okay, So this step or size I am defining as, maybe let's define h. Okay, so h is the length of each of the subintervals. So this is my 1 by n, the other would be 2 by n, 3 by n, and so on. At last, at nth level, you will get n by n, which is your 1. Okay, so this is how we are defining this partition. Now you note that as n goes to infinity, this size of the interval, subintervals, will converge to 0, right? So it will become more and more compact. I mean, the smaller. As n increases, the size of the subinterval will decrease, and it will eventually go to 0. Okay. So this is what I will do. So our interval, so for this n, I am defining. So let then consider partition Pn as, so this is x0 is 0. Maybe how should I write? Okay, I'll just write the directly this one, 1 by n. So sorry, first include 0, then 1 by n, 2 by n, dot 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 till 1. Okay, so this is the partition. Now see what I was telling, that the, okay, so here I am taking the size of each of the subinterval is uniform, right? All the subinterval has the same length. So the norm of this interval or this partition, okay, so the norm is the maximum length of the subinterval. So over here all the subinterval has the same length. So in this case the norm would be 1 by n, right? So this is how we define the norm. Norm is basically the maximum length of the subinterval in the partition. Okay, so this norm of this partition is 1 by n. Now let's try to calculate what is UFPN. Okay, so what is the definition? So I'll just copy it from here. So for this infimum, you just replace by supremum. Okay, now you see the supremum of this function in the interval 1 by n to 2 by n. What will be the supremum of this function? You see, in each of this subinterval, you know, at the, so let's consider this any one of the subinterval, maybe I should write here. So say this is 1 by n to 2 by n. Okay, at the irrational points, the function is taking the value 0, so we don't have to worry about that. And for the rational points, it is taking the value x. Okay, so it's something like, so this is the largest value, right? What the function takes over here, isn't it? So the supremum of this function, sorry, on each of this subinterval, so let's say this is k by n to k plus, or I by n to I plus 1 by n, right? So this is the xi and this is xi plus 1, right? So in this subinterval, the maximum value of the function will be achieved at this point. So that's what I'll write. So the maximum value will be achieved at that, and that function is given by x. F of x is x at that point, because these are the rational points. So that I'll write. So summation I from 0 to n minus 1. Then you have I plus 1 upon n. And then what will be the length? Length would be 1 by n, right? So this is nothing but 1 by n square I'll take outside. And then summation you have I plus 1. So I'm replacing I plus 1 by some new variable. I'm calling it, maybe let's say I'll call it j. So j is nothing but I plus 1. So then j will vary from 1 to capital N, right? Because I is varying from 0 to n minus 1. Now this summation, so this is 1 by n square. Now this summation will be given by n into n plus 1 upon 2, right? So now what you have is, this is n square plus n by 2. So n square will cancel, so I'll get 1 by 2, and the next term would be 1 by 2n, right? So this UFPN evaluates to half plus 1 by 2n. Okay, now if you want to look what will be UF, okay, so there is another way of calculating this UF, is like you consider a sequence of partition and consider the norm of the partition as goes to 0. So this is, let me write in this way. So this is UFPN, okay, and you take limit norm of Pn, or what should I say? Okay, so basically when the norm of the partition what we are choosing, that should converge to 0. Okay, then that converges, this UFPN will converge to UF. Okay, so this is another way of evaluating this U of F or any L of F as well. Okay, so in this case we can see that as n goes to infinity, okay, this is same as saying that the norm of Pn, which is 1 by n, this goes to 0, right? So I can write this UF as the limit of this UFPN. Okay, now in this case you can clearly see that this is nothing but half. So your upper integral 0 1 f, this is turning out to be half, while the lower integral was coming to be 0. Correct? So clearly these two values are not equal, so the function is not Riemann integrable. So what you can conclude is that U of f, which is equal to half, is not equal to 0, which is L of f, and this tells you that f is not Riemann integrable. Okay, is this clear? So the correct option would be this, and that's all. So here f is missing. Is this clear? Okay. Okay, so this was a basic problem related to integrability. Okay, so now this is another problem. So over here you have been given that the function f is a continuous function on any interval a comma b, closed interval. So you have to show that there will exist a point C in AB such that this integral value, okay, is equal to fc times b minus a. In other words, what you can rewrite this as, this 1 by b minus a, this f of x d of x ab, this is equal to f of c. Okay, so this is nothing but what, so this is basically the average of the function. Okay, our average, this is sometimes also denoted by this average sign. So this cross or this straight line, this one represents the average. So average of, sorry, so this average integral of the function f. Okay, so you integrate on the whole region and then you divide by the length of the interval. So that's the average. Okay, so it says that there will exist a point C in AB such that this average value will be achieved by the function. Okay, so this is the problem. Now you can clearly understand, like the way I have written here, now it should be clear that how we should approach. Can you get some hint like how to approach this problem, or what theorem one should use to get to such to such identity? Okay, so let's try to see. So the way I have written here, you can clearly see that if you can show that this value, this average integral, lies between two function values. So suppose if I show that this average integral AB f lies between, say, let's say FB and FA, okay, something like this, okay, or anything, it need not be AB, so some x0, some x1, okay. If I can show that this average value lies between two functions value, then you can directly use the intermediate value property of the function f, because it is a continuous function, to conclude this one, right? So this is the main idea to prove this one. Okay, you just have to use the intermediate value property and you will get this one. Okay, so let's try to see how to do that. Okay. So this function is a continuous function on a compact domain, right? AB is a closed and bounded interval. So in this compact set, since it is a continuous function, it will achieve the maximum value and the minimum value, right? This is what you know, that any continuous function defined on a closed bounded interval achieves its maximum value and minimum value at some point, right? So we'll do now denote. So let what should I write? So okay, so let K exist, or how should I write? Okay, so let suppose x0 x1 belong to AB such that f of x0 is the infimum of the function f of x where x belong to a comma b. Okay, so at x0 the function is achieving its minimum value, and at x1 it will achieve the maximum value or the supremum, a comma b. Okay, so this is how I am defining this x0 and x1. So I am choosing this x0 x1 where it achieves the and existence of, so okay, so such existence of x0 and x1 is guaranteed because the function f is continuous on closed and bounded interval AB. Set a comma b. Okay, so such thing can be guaranteed. Okay, so now what you can write is that f of x0, this is less than or equal to f of x, right? And this is less than equal to f of x1, and this is true for all x belonging to a comma b. Correct? Now you know that the function f is continuous, so it is integrable, right? So it is an integrable function on AB. So now I'll just integrate. So on integrating with respect to x. Okay, so once when you integrate it, you see this is a constant value. So when you integrate it over any interval AB, then that would nothing but this value times b minus a. Okay, so there is one more remark I should mention. Okay, so just a second. So see, it could be possible that the function is constant. So in that case, this fx0 and fx1, so x0 and x1 would be the same thing, right? So here I should mention at one point. Okay, so maybe if x1 is equal to x0, then f is a constant function, and so see, when the function is constant, so this will be some value alpha, and this f is also alpha. Now when you integrate it over AB, you will get alpha times b minus a. So it is obviously true, correct? So when it is constant and the identity holds trivially. Okay, so there is nothing to prove here. So therefore we will assume now if, so let x0 is not equal to x1. Okay, and without loss of generality, let's assume that x0 is less than x1. Okay, so without loss of generality, assume x0 is less than x1. Okay, okay, so now if we integrate this inequality with respect to x, so what we get is, so this would be nothing but f of x naught, and then you multiply with the length of the interval, which is b minus a, right? And then this is less than equal to f integrate over a and b, and this is less than equal to f of x1 times b minus a, right? So this is, we have just integrated the above inequality. Now you just divide by b minus a, so what you get is f of x0 is less than equal to 1 by b minus a, f ab, this is f of x1. Now you just use the intermediate value property of the function f. Okay, so thus now by intermediate value theorem for the function f, of the function f gives the existence of c belonging to this x0 comma x1, which is obviously subset of a comma b, right, satisfying f of c equals to 1 by b minus a integral ab f. So this is how you can prove this identity. Okay, so you just have to use the continuity of the function. That's all you needed. Continuity of the function and the compact interval. Okay, I hope this is clear. Okay, so now let's move to this problem. So over here you again have this function defined in this particular fashion. Okay, then you have to check the integrability of this function. Okay, so let's try to look how the function looks. So it's taking the value 0 at x equal to 0, and in the interval, so you can clearly see. Okay, so this function is, so this function is defined on 0 1. Okay, so f is from 0 1 to r and is given by this. Okay, so at 0 the functional value is 0. Okay, now if you look at this interval, so let's take for n equal to 1, so we'll have 1 and then half. So in this interval the function is taking the value 1, right? It's like this. So in half to 1 by 3, so maybe I should make it somewhere here. So in this interval the function is taking the value half. In this 1 by 4 to 1 by 3 the function is taking the value 1 by 3. So this is how the function is defined. Okay, and this will eventually go to 0. So it is defined in the whole domain 0 1. Okay, so now you, to check the integrability, again you have to do the same thing. Okay, so first let us try to see. So again we will consider a partition. Okay, and then try to see how the upper sum and the lower sum looks. Okay, so let us write the functions. Okay, so you already understood. So fx is nothing but 0 at x equal to 0. It is taking the value 1 when x is half, so half excluded, and then x less than equal to 1 by 2 when you have this value. Okay, so and so on. Now if you want to integrate this function f over 0 1, what you do, you just try to split this whole interval, right? So you can write this as, it is from 1 by n plus 1 to 1 by n, where n will be starting from 1 to infinity, right? This is how we define. Then this whole 0 1 interval will be covered by this kind of interval. So maybe I should write somewhere. So this 0 1 interval, you can write it as 0 and then union, this union n from 1 to infinity. Okay, so let me not put this bracket, just this one, and then 1 by n to 1 by n, right? This is how then it will converge. This whole 0 1 will be given by this. Okay, then we can write this in this fashion, and I think you can remove this 0 as well. No, but then it will, okay, so you can check that this union will be just open 0 closed 1. Okay, so you have to include this 0 probably. Okay, anyway, so we don't care about one point when we are talking about integration, so we can not consider it, we can just leave it. So this is how you can write this 0 1 integral like this. And now in this interval the function is taking the value 1 by n, right? So this is from n from 1 to infinity. Now this functional value is independent of, so maybe I should write, so it is obviously independent of the variable over which we are integrating. So maybe I should write, let's say dt. Okay, so you can write 1 by n outside, and then this will be 1 by n minus 1 by n plus 1. Now when you add it up, when you multiply this, so you'll get 1 by n square, n from 1 to infinity, and then the next would be minus, so this is 1 by n times n plus 1. Okay, and this is from 1 to infinity. Now you, this product term, this summation, you can write it as a telescopic sum, right? So this can be written as summation 1 by n square with minus and then summation. This can be broken as 1 by n, 1 by n plus 1, and then you have minus, right? Plus 1 minus n, correct? So this is how you can write. So this is starting from n equal to 1 to infinity. Now you can clearly see these terms will be, so if you try to expand it, what you get is 1 minus half, right, plus half minus 1 by 3 plus 1 by 3 minus 1 by 4 and so on, right? So you can clearly see there is a cancellation. So what will survive is just 1. Okay, so this would be, this whole thing will give you the value 1, and this 1 by n square you already know that this is a convergence series, and the value to which it converges pi square by 6, and this is 1. So this will be the value of this integration. Okay, so here I have used a lot of things. So here I have used the argument that the function is constant, so it is integrable in this interval. So I can, if you want, I can write, so f, okay, is constant on, so there is, okay, so if you really want to write properly, then what you can do is, maybe I have skipped a lot of things, I have written it vaguely, but although it's perfect, okay, as part of solution, but if you want, you can write in this fashion as well. You can define this phi n, okay, from, let's say, 1 by n plus 1 to this 1 by n, okay, to r, and you can say this phi n of x, phi n of x will be just 1 by n. Okay, and then you can say that f or phi n is equal to f when you use, okay, on this interval 1 by n plus 1 to 1 by n, okay, on this closed interval. Maybe you can define it on the whole closed. Okay, and you know this is constant, so it is integrable. Okay, and you know that phi n is equal to this except one point, which is 1 by n plus 1. Okay, so this integration of phi n will be same as integration of f on this interval. This is the way you can write, but this is also correct. Okay, so this is one way. If you want to write properly, you can write it in this fashion as well. Okay, so you break, so here instead of write, so here the first step would be I'll write f, then I'll replace this by phi n. Okay, and I know this integration value will be this, and so on. So it's just a way of writing, but this solution is also correct. Okay, is this fine? Okay. Okay, so let's move to this problem. So over here you have been given a function which is defined from a closed interval a b. Okay, and this is non-negative function. So this is very important. So this f of x is greater than equal to 0 for all x defined on this closed interval a b. Okay, so the function is continuous and non-negative such that this integral, okay, is turning out to be 0. Then what you have to prove is that this function is actually identically equal to 0. So this function cannot take any non-zero value. Okay, so this is the first part. The second part tells you that is this continuity required. What if we drop the continuity condition? So suppose if I just say that f is a non-negative function with integral equal to 0, can you say that the function is identically 0? So this is the second part. The third part tells you that what if I remove this non-negativity condition? So instead of this, I have just the, okay, f is just a real valued function which is continuous and the integral of f is 0. Now can you say that the function will be identically 0? So these are the two very important conditions that has been put over here. Okay, and the answer to these two question is in negation. So the result won't be true if I remove either this or this. Okay, that we'll see. Okay, so let us first try to solve the first part. Okay, so do you have any idea like how to prove this? No? Okay, so the proof of this problem is basically you can do it by contradiction. Okay, so what we will do, so see what I'll assume is, so I'll just sketch the proof and then I'll write it properly. So this is your AB and the question is that f has to be 0 on this whole interval. So what I'll say that, okay, let's say that there exists some point here x0 where it is non-zero. That non-zero means that it has to be greater than 0. So such that f of x0 is greater than 0 because it is a non-negative function. So it cannot be negative. So f of x0 is greater than 0. Now using the continuity you can say that there will exist a neighborhood. Okay, if a function is strictly positive at this point, then due to continuity there will exist a neighborhood where the function would be strictly positive. Okay, so f will be strictly positive in this interval. Now it's obvious. Then you can say that this integral AB, okay, now you can write this as say on this neighborhood n f and then on the complement n complement f. Now about this you don't care. So this is obviously, since the function is greater than equal to 0, this integral has to be greater than equal to 0. But due to the fact that this f is strictly positive in this neighborhood, it will be strictly positive and the sum of these two numbers will be strictly positive, and this is a contradiction because what you have been given is that this integral is equal to 0, but what you have obtained is that the integral is strictly positive, which is a contradiction. Okay, so this is how you can prove this part. Okay, so I'll tell you one more thing maybe. So over here you see that, okay, let me keep it as it is. So what you can do here, instead of assuming this to be greater than 0, what if, so suppose instead of this condition I am saying that this is minus infinity to 0, so that is it is non-positive function, then also the result holds true. Okay, it's just that it has to be of one sign. The function has to maintain one sign in the whole interval. Okay, so now if I assume that if it is negative, then the same argument would work. So now you will have, you will have f of x0 is less than 0. Again by this continuity you will have f of x is less than 0, again here what you will have is that this is less than 0, this is less than equal to 0, and ultimately you will get less than 0, which is a contradiction. Okay, so the proof is same for both of the part. Okay, so this is how you will try to prove. Okay, now let's come to the proof. Okay, so let us say that suppose, so prove by contradiction maybe. If possible, suppose f is not identically 0. What does this mean? That is, or not that is, so this implies there exists some x naught in the interval AB such that f of x naught is strictly greater than 0. Okay, now do you know the proof? That I think I might have discussed that if f of x naught is positive, then there exists a neighborhood because of continuity where the function is positive. So do you know the proof, or should I write it here? Okay, so I'll write it. Okay, so you have assumed that there exists x naught such that f of x naught is strictly greater than 0. Now, as f is continuous on this whole interval AB, so in particular at x naught, so this is in particular. Okay, so for epsilon equal to f of x naught by 2, there exists delta greater than 0 such that f of x minus f of x naught is less than epsilon, which is f of x naught by 2, if my x lies in a delta neighborhood of x naught. And this is nothing but it tells you that f of x naught by f of x naught by 2 less than f of x, and this is less than 3 of f of x naught by 2 if x minus x naught is less than delta. Okay, so this function is strictly positive because this is strictly positive, right? Okay, so we have got a neighborhood where this function is strictly positive, or okay, we have a particular bound as well. Okay, so now let's say this is 1. Now this interval AB, this can be written as a to, let's say, x naught minus delta f plus x naught minus delta to x naught plus delta plus x naught plus delta to b. So I have broken the interval in 3 sub-intervals. Now this, you know, this is greater than equal to 0. This also, you know, this is greater than 0 since f is greater than equal to 0. Okay, so this is greater than equal to 0 plus over here we have a bound that this is greater than f of x naught by 2. This is f of x naught by 2, and then this length of this interval. So length of this interval is given by 2 delta plus 0, right? And this is nothing but greater than equal to delta times f of x naught, and this is greater strictly positive, right? So what you have got is that this integral is strictly greater than 0. This is a contradiction, right? This is a contradiction. Hence f is identically equal to 0. Okay, so this is how you can prove this, and as I mentioned, you can remove the condition 0 infinity by this as well. What about the second part? So I have already mentioned that the answer would be no. Okay, so if we drop the continuity condition, then the result won't be true. So do you have some example in your mind? So what you have to find, I'll just write it precisely. So goal, so the answer is no. Okay, and the goal is find a function f from AB, okay, which is defined. Okay, so AB you can choose particularly. Okay, so which is a non-negative function such that the integral of f is equal to 0, but f is not identically 0. Okay, and f is continuous. Okay, here you are dropping the continuity condition. Okay, so I'm not saying that the function f is continuous. So you have to go for some discontinuous function, right? Such that the integral is 0. So can you think of some example?
Dirichlet function.
Dirichlet function. Okay, so what is that function? Can you tell me precisely? So f from where to where you want to define? You're correct actually. Maybe you can tell me.
R to 0 comma 1.
Okay, you want to define. So let's restrict to some compact set. So let's say it's from 0 1 to 0 infinity, right? And what is the function?
Zero if x belongs to Q.
Okay, that, okay, you are talking about that function. Okay, so 0 if x belong to 0 1 intersection Q, and what other value you want to put? So 1, let's say. But then this is not integrable, right? I think we proved it here. This was our first example. Right, so here you are just taking, okay, in this case I guess it would be just, let me check. Is it Riemann integrable? No, I don't think it was. No, this is not Riemann integrable, right? Because the lower sum is always going to be 0 and the upper sum would be 1, right? Okay, so you can take just a simple case. Okay, so maybe you put 0. So define the function to be 0 when x is not equal to 0 or x belong to any point. You just leave one point because we know that one point does not change the integration value, right? So we'll say it's in 0 comma 1 and you define it to be 1 when x is equal to 0, let's say. Okay, if we define it in this way, you can clearly see that it is a discontinuous function, obviously, that the function f is discontinuous at 0. Obviously if it is continuous, then the result is obviously true. So we are looking for a discontinuous function if we want to get a counter example. So we have this example. You can clearly see that the integral of f is 0, but f is not identically 0, right? Because f at 0 is equal to 1, which is non-zero value. Okay, so this is how you can look for this example. Is this clear? Okay, now let's come to the C part. The C part tells you that, okay, so the answer of C is also no. Okay, and here the goal would be to find a continuous function f which is defined from AB to, let's say, R. Okay, so here we don't have any restriction on the sign, such that this integral of f is 0, but f is non-zero. Can you think of some example? This should be very easy, right? And there are many well-known functions that you know. Okay, so let me what about this function? Sine function I am taking. So although it does not look like sine function, but still. This is 0, this is pi, this is 2 pi. There's some loss of symmetricity. What about this function? This function is continuous, right? So I am writing this f is from minus pi to pi to r. F of x is equal to sine of x. Now if you integrate this function f from minus pi to pi, right, here it is taking the positive value. Okay, so and the integration value you can check that whatever, suppose this integration of this or the area, let's say this is alpha, then this would be minus of alpha, right? So the sum of these two values will turn out to be 0. So the integral of f would be 0, but clearly f is not 0. So f is vanishing just at 3 points, 0, pi and 2 pi. Other than these 3 points, the function is non-zero and f is non-zero. Okay, so this is one. You can think of many examples. Maybe you can think of examples like this kind of anything. It just has to be continuous, just so that this is what we are demanding. So here the area, what area will be there, this would be just negative of that area. So that's why maintaining one sign is very important. Otherwise the result will fail. Okay, so that's why we need just the graph has to lie either on the above of the x-axis or below x-axis, so that there is no cancellation as such. Okay, here you can clearly see there is a cancellation. You can think of this example x cube as well, right? So if you think of x cube from, let's say, 1 to minus 1, then the area here would be just negative value of the area covered here. Again there would be a cancellation and the integral will be 0. So there are many examples, and there are many well-known examples that you know. Okay, so you can think of other examples as well. Okay, so now let's come to the next problem. This is an easy example. So you have this box function defined from 0, 3 to r. Okay, so let me first write what this function would be. So f of x will be taking the value 0 if you take x from 0 and less than 1. It will take the value 1 if you start from 1 and less than 2. It will take the value 2 if you start from 3, and it will take the value 3 if your x is equal to 3. So this is the function. Okay, so now you can clearly see that the function is continuous except 1, 2 and 3, right? So f is a continuous function, is a bounded continuous function, is bounded and continuous on 0, 3 minus 1, 2 and 3. So there are 3 points of discontinuity. So that will not matter. So this would imply that f is Riemann integrable. Right? So f is almost everywhere continuous. So it is Riemann integrable. Okay. Now what would be the integral value? Again you can do the same kind of argument. You can define phi1, phi2, phi3 if you want. But I am not going to do that. So you can just write f from 0, 1, 0 to 3, same as 0 to 1, 1 to 2, 2 to 3, right? And this would be, so the first integral would be just 0. This is 1 times 2 minus 1. This would be 2 times 3 minus 2. So what you get is 3. Okay, is this fine? Okay, so now let's come to this one. So suppose you have been given a function f which is defined from a compact interval a b to r such that the f square is integrable. Okay, so can you say that the function f is also Riemann integrable? So one way is right? So I'll just mention. So suppose f is a bounded integrable function. I hope you must have seen this result. Then you can prove that f square and mod f, okay, so here I am talking about this mod, so this are Riemann integrable. I won't prove it, but you can see. I hope that you must have seen these kind of standard results. So if f is integrable, then this f square and mod f is also Riemann integrable. Okay, but now I am talking about the converse. That suppose that f square or mod f, any one of them, are Riemann integrable, then can you conclude that f is also Riemann integrable? Can you suggest some example?
No, sir.
No, okay. So what will do the example? So if you want to disprove it, can you give some example for that?
X square.
You are saying f of x equal to x square. Is this what you are saying?
Yes, sir.
Okay, so f square would be x4, right? This is Riemann integrable.
Yep. Take f to be x.
Yeah, so still, okay, so f of x, then f square would be x square. So this is Riemann integrable, this is also Riemann integrable, right? So are you saying that is it true or is it false? What do you want to say?
False, sir.
False. Then you have to give an example where f is not Riemann integrable, but f square is Riemann integrable, right? Here both of the functions are Riemann integrable. So that cannot serve as a counter example. So can you think of example? So you already hinted, like in the last example what you were giving, similar kind of example would work here, right? Can you think of some example now? Such examples we have seen a lot of times.
Dirichlet function, sir.
Yeah, so what will be the function? Can you tell me?
0 if f belongs to.
Okay, 0 if x belong to.
0, 1 intersection q,
And then on irrational, what do you want?
x.
Okay, so now if I do f square, it would be the same kind of function, right? 0x square. So again it won't be Riemann integrable. So you have to think of function f so that the f square becomes Riemann integrable, right? Can you recall some example that we have seen? Okay, so maybe I just give example. Okay, so forget about x. Okay, Now give me some example so that the f square become constant. So here, like if I choose like this, then okay, this f is not Riemann integrable, but f square is also not Riemann integrable. What if I choose my this z, instead of 0 and x, I choose some value so that the f square becomes constant? Can you think now?
+1, -1.
Exactly. So suppose if I put the value 1 here and -1 here, then you can clearly see the f square is, and same for mod f as well. So mod f of x is same as f square of x and will be equal to 1 for all x belonging to 0 comma 1. So clearly you can see, so f is not Riemann integral, so f square and f mod f are Riemann integrable on 0 1, but f is not Riemann integrable. Okay. Okay, so now let's move to this problem. Okay, so here the question is that suppose you have a function f which is Riemann integrable. Now can you say that the, okay, and assume that it is strictly positive, it is not going to be 0 at any point. Now can you say that 1 by f is also going to be Riemann integrable?
It is not Riemann integrable, sir.
1 by f.
If you take f of x to be x, then 1 by f of x will be 1 by x on closed interval 0 comma 1.
Okay, so okay, let me, okay, so let me think. So f of x, you are saying x when x is in 0 comma 1, right? So in this case 1 by f is not defined, right? How would you define 1 by f here? Because f at 0 will be 0. But you can change it a bit, right? You are going in a right direction. Okay, so what you are suggesting is actually correct. So
if you define singularities x minus 1 on closed interval 1 comma 2.
no, then 1 by x if you take, then that will be also integrable, right? Okay, so if you are saying that if I change 1 comma 2, then in 1 comma 2 1 by x is also integrable because it's a continuous function on this 1 by 2, 1 comma 2, it is also integrable. What you are looking here, like what you are saying, that the singularity, that will help actually, because the function becomes unbounded, right? So maybe what you can do is, so you can define it in this way. So f from 0 1 to r, okay, you define f of x as, so you define it to be x when x belong to open 0 closed 1, and at 0 you define some other value because the function did not be continuous, you don't want continuity there, so you can define it anything. So let's say 1 when x is equal to 0, right? Now this f is obviously integrable because one value does not matter, so you can clearly see f is continuous on 0 1 except the point 0, so this implies f is Riemann integrable. Now what will be 1 by f? So 1 by f, again it's defined from 0 1 to r, and 1 by f of x would be given by, so it would be 1 by x when x is in the open interval 0 closed 1, and it would be 1 when x is equal to 0. Now you can clearly see that this function is not Riemann integrable, right? Because it is unbounded. Okay, so maybe how I can explain is, so suppose you take any partition, okay, so let So how the partition would look? So 0 is equal to x0 less than x1, x2, x capital N equal to 1. Okay, if I choose, then how you will define this UFP? Let's say UFP would be the summation. You take supremum of the function on this xi to xi plus 1 of the function f of f, and you subtract xi plus 1 minus xi. So this I is from 0 to n minus 1. Okay, now you tell me, if I concentrate on x0, x1, okay, so concentrate, okay, let me just write here. So if you just concentrate on x0 comma x1, okay, so x0 is 0. So if you take this interval, so you let me draw the graph first. So how this 1 by x will look? So 1 by x is like this, right? So as x goes to 0, this 1 by x will converge to infinity, right? So whatever interval you choose, so let's say this is x0 and this is x1 is any point just greater than 0. If you choose in this interval, what will be the supremum of this? This is going to be infinity. And after this, everything is finite, right? So you can write it in this way as well. So if I break it this up, so maybe, so let me say this is I from 1 to this, and one case would be the supremum of x0 to x1 f, right, times x1 and times x1, because okay, x1 minus x0, x0 is 0 but still okay. Now you can clearly see this is a finite value. This will be some c, because on each of the subinterval the function is bounded, so it is going to take some finite value, and this is also a finite real number, so this whole summation will be a finite number, okay, obviously depending on n, but this is always going to be infinity, in particular this one, this supremum, because this function is unbounded. So this UFP is always going to be infinity, right? So this tells you that f is not, sorry, 1 by f, this is 1 by f. This tells you that 1 by f is not integrable. So your idea was correct, that you have to do something which blows up, so which is unbounded basically, right? Okay, I hope this is correct. Is this fine? Okay, so now let's proceed to the next problem. Okay, so suppose you have this function f and g, which are Riemann integrable function, and f of ab is contained in CD, which is the domain of g. So basically you can define the composition G composed f. So this condition tells you that G composed f is well defined. Okay, so G composed f makes sense. Then if f and g are Riemann integrable, can you say that G composed f is also Riemann integrable? So that's the question, that composition of two Riemann integrable function, does it give you a Riemann integrable function? Okay, what do you think?
Yes, sir.
Yes, okay, so do you have a proof? Or have you seen such results? This is why you are saying this? So actually this statement is not true, that composition of two Riemann integrable need not be Riemann integrable. Okay, I'll give you an example. But it becomes, okay, so the correct statement is this one, that in this condition, if you add Okay, so if you add here that G is continuous, then you can say that the composition G composed F is Riemann integrable. Okay, I'll not give you the proof, but you can check in book. I hope you'll get the proof. Okay, so if the function G, okay, which acts afterwards, so F is the function which acts at the very beginning, and then G acts on F of x, right? So G is evaluated at F of x. So if the first function or the function which acts later on, if that is continuous, then you say that G composed F is Riemann integrable. Okay, but in general this is not true, and this is the example. So you construct this function F from 0 1 to R. Okay, so basically you have to choose a Riemann integrable function. So what you can do is you can define F of x to be, so I think we already did this example. Let me see if I have written it above or not. This 1 by n was one function, right? Yeah, this function, but I mean not exactly this function, but this will also, okay, so this will not work precisely, but okay, in this kind of function. So let me write the proper definition. So this would be 1 by n, okay, if my x is the rational, actually it's the basically the Thom function, right? So m by n Thom function, I think I have discussed in the continuity section, I guess. So m by n you choose, so where m is, okay, so m is in this integer and n is natural number, and GCD of m comma n is equal to 1. Okay, and you take it 0 when x is irrational. Okay, then okay, so now you see this Thom function, this was already discussed, so I'll just write this line. So what we have seen in this one, that f was discontinuous only at the rational points, right? If you can recall, this function f is discontinuous only at rationals, right? And you know that the rational number is countable. So, and rational or set of rational number is countable. So what you can conclude is that so f is continuous almost everywhere, right? And this tells you that f is Riemann integrable on 0 1. On 0 1 almost everywhere, right? Now g would be a simpler function, it's not that complicated. So g you can define from 0 1 to R, so that g of x, what you do, it will take the value 1 everywhere, okay, except the 0. So if x belong to 0 comma 1, it will be 0 if x is equal to 0. Okay, so this is a non-trivial function, but okay, once you know, you can just try to remember it maybe. So now this g's function which is taking the value 1, now you can clearly see this is obviously, this is integrable, but this is just a constant function except 1 point, so it is Riemann integrable. But now if you see the composition, so g composed f is what? You can clearly see that the range of f is just contained in 0 comma 1, right? So okay, so I should write this line. So f of 0 comma 1 is contained in 0 comma 1, Okay, so G composed F we can define, and G composed F you try to see from 0 1 to R, okay, given by G composed F of X. Okay, so see, when X is a rational number, okay, in particular of the form m by n, then F will take the value 1 by n, correct? And this 1 by n, because this 1 by n belong to this interval 0 1, that will give you the output 1. So it is going to be 1 if X belong to 0 1 intersection Q, okay. And if you take any irrational number, then F is taking the value 0, and 0 is being mapped to 0 by G. So it is going to be 0 if X belong to 0 1 intersection Q complement. Is this okay? So if you take any rational number, this F is taking the value 1 by n, and this 1 by n, since it lies in this interval 0 1, it is giving the value 1. So the for composition will give the value 1 when X is rational. If you choose any irrational number from here, then F is taking the value 0, and when G acts on 0, it gives you 0. So that's why it's coming out to be 0. Now this we have already seen that this is not integrable, maybe in the first problem I guess, but G composed F is not Riemann integrable, and this we have seen in question 1. Okay. Okay. Okay, so now let's come to this problem. So suppose you have a function f which is defined from AB to R, which is a bounded function, and the condition what is given to you is that if you choose any point from the open interval AB, okay, such that the f is integrable on this C comma B. Okay, so let me describe it. So this is your AB, okay, AB. F has a property, so f is a bounded function, okay, and it has the property that if you choose any C in between this AB, then f is integrable on this interval, and this is true for any C. Okay, if you choose any C, okay, C cannot be A. If C is equal to A, then it's done. Okay, so it is true for any C. So you have to prove from here that it is integrable on A comma B. Okay, it is given that for any C, f is integrable on C comma B, but C has to be from open interval A comma B. Then you have to prove that f is integrable on AB. This is the first part. Okay. The second part tells you that, okay, instead of this, what you have is that suppose you have this interval AB, and it tells you that for any D, so if you choose any D, okay, from here, whatever point you choose, that is integrable. Okay, so the function f is integrable on A comma D for any D you choose. Then you have to prove that it is integrable on A comma B. Okay, and third tells you, so this is about A and this is about B. The third tells you that the function has the following property, that if you choose AB is given to you, it tells you that if you choose any 2 points in this AB interval, then the function f is integrable. So whatever point you choose, this function is integrable on C comma D for any CD in between AB. Then you have to prove that the function is integrable on AB. So this is the problem that you have. So all three look similar. So in fact the first part I'll prove, okay. The second part you can do in a similar fashion, and the third part is nothing but it's just a corollary of A and B. Okay, C part is just obvious. If you prove A and B, then C is just an implication from that. Okay. Okay, so let us try to prove the A part first. Okay, so what you have to do is, so you have to prove that it's integrability at A. Okay, so what you can do is you can choose a sequence of points which converges to A. Okay, and it is not, obviously it is not A, so each of the sequential terms should not be A. Okay, so okay, so before going that, what does this integrability means? Integrability means that the upper Darbox sum and the lower Darbox sum, you can make it as close as you want. So for any epsilon there exists a p epsilon, so there exists a partition such that this UFP epsilon minus LFP epsilon is less than epsilon, right? So this is what our goal is to prove. Okay, so let's keep that in mind. So now to prove that, so we'll first choose an epsilon. So let epsilon greater than 0 be any real number. Okay, now goal would be to find a partition P such that UFP minus LFP is less than epsilon. Okay, so this is what we have to prove. Okay, so now as I suggested that we want to prove integrability at A, so we'll take a sequence. Okay, so consider a sequence Cn, and I'll have to take it in the open interval AB, because I will use the fact that the function is integrable on C comma D for any C belonging to the open interval A comma B. Okay, so we'll choose a sequence Cn in A comma B such that Cn converges to A. Okay, and you can obviously choose such sequences, right? One particular sequence would be just A plus 1 by n. So this sequence obviously converges to A. That is a very obvious sequence. Okay, so such sequence exists, so I'm choosing one sequence. Okay, then there exists a capital N, right, such that this Cn minus A is less than, okay, so this is some, so I'll have to choose what this epsilon, so I'll just leave this gap, is less than whatever we want, right? So there exists N, maybe I should write for epsilon equal to something, for epsilon tilde, let's say something, there exists N such that this Cn minus A is less than epsilon tilde. So we'll see what this epsilon tilde is for all n greater than equal to this capital N, right? Okay, so we'll just talk about this capital N now. So as of now we'll just talk about this capital N. So in particular what we have is this C at capital N minus A is less than epsilon tilde. Okay, now we know that this function, okay, now this f is Riemann integrable on Cn comma B, right, by the assumption that we have this is Riemann integrable on this. This implies there exists a partition Q such that this U of F Q, so Q of this C and B, such that UFQ minus LFQ is less than epsilon by 2. Okay, so this is obvious because okay, as of now if you don't want, let me put it, so you can make it as small as you want. Okay, so maybe this is, let's say, epsilon hat. Okay, now what you wanted, so now we'll consider a partition for AB. So let P, I'm defining a partition P, so such that this A I'm adding in this Q. Okay, the Q was a partition of C and B. Okay, so you remember that this was my A, this is B, and Cn is somewhere here. So Q partitions this interval, so Cn, this we have. Now I'm defining P as the partition A, this. So this is my new P. Okay, so now this P is a partition of AB. Right? So I'm defining this partition, I'm considering this one. Okay, now let us try to evaluate what is UFP minus LFP. Okay, so this is nothing but, the first thing would be that supremum of F over A comma, so Q, okay, if you want to, so Q is start with from Cn, so I'll just write Cn, supremum of the function F, and then you have Cn minus A, right? And then plus UFQ, right? Because the other partition points are the same. So if you add it up, you will get UFQ. Okay. Now minus for this one, you will have infimum over A comma Cn of F multiplied with Cn minus A. And the rest would be L of just F comma Q. Okay, now if you just add this up, so what you get is the supremum minus infimum, and then you take a Cn minus A common, so this you can write it as, okay, so maybe, okay, I have not denoted it, so maybe you can, since this is a bounded function, okay, so let me first write this, then I will come to that, or let me mention it somewhere. So I am assuming that m is the infimum of the function, m less than f of x, so for all x in AB. Okay, this is because f is given to be bounded. This one maybe I can, okay, so now this supremum I can bound it by capital M, right? Because that is the supremum of the whole interval AB. So that I am bounding by M, and then, okay, so first let me write this. This is a common, then I will do that. A comma Cn F minus infimum A comma Cn F, and then you take Cn minus A outside. Okay, and then you have this LFP, so this is equal to P minus, sorry, UFP minus UFQ minus LFQ. Okay. Okay, now as I was saying that this supremum can be bounded by M, and this minus of infimum can be bounded by minus of M. So this I can write this as M minus M times Cn minus A. Okay, so this is something, you know, that Cn minus A is in my hand, so I have chosen, you remember from here that the Cn minus A is less than epsilon tilde. So now it's time to choose what epsilon tilde I should choose. Okay, so let me first write this one, then we'll come to that. Cn minus A plus, so UFQ minus LFQ. Again, this I can make as small as I want, right? Okay, so you see, if I make this less than epsilon by 2, and this one, so let me write this I'll try to make less than epsilon by 2, this I'll try to make less than epsilon by 2, and times this thing what I have here, right? I'll divide it by 1 by m minus m. Then you see this whole thing will come as epsilon by 2 plus epsilon by 2, which is equal to epsilon, and this is what we wanted to prove, right? So that's why this is my epsilon tilde and this is my epsilon hat. Okay, so now I'll just substitute. So here I'll get epsilon by 2. Okay, here I can write epsilon tilde would be epsilon by 2 m minus m, 2 m minus m, epsilon by 2 m minus m. Okay, so ultimately you got that we have got a partition P, okay, such that this u of fp minus L of fp has turned out to be less than epsilon, and this proves that f is Riemann integrable. Okay, in a similar fashion you can prove the B part. So the B part can also be proven in the same way. Now you will take a sequence Dn, okay, that converges to B. So I'll just write maybe sketch. So here also you'll take a Dn which converges to B. Use so this Dn, so minus B will be less than epsilon by 2 m minus m. Okay, and use integrability of f on dn comma b. Am I writing it correct? Sorry, a comma dn to get a partition Q such that this u of f comma q minus L of f comma q is less than epsilon by 2. You define a partition P which will be nothing but Q, and you just add B, then you check UFP minus LFP will be less than epsilon, and this will prove you F is integrable on AB. Okay, so this is just the same line of argument would work here, but now let's come to the C. Okay, C is quite interesting. So C you just have to prove using A and B. Okay, so the argument would be very similar. So I'll just repeat what C means. So C is telling you that if you have in this interval AB, it says that if you choose any CD in between AB, then F is integrable here. Now from here you have to conclude F is integrable on AB. So can you suggest some idea how to do this? No? Okay, so what we'll do is basically, so instead of working on this whole AB, what I'll do, I'll split the interval. Okay, so let's say this is the midpoint, so A plus B by 2. Okay, now I'll fix this point. Okay, so this is my new D, let's say. So I'm just talking about this part only. Let's stick to this part. What I know that according to the property of the function, I know that my function f is integrable on this one, on c comma a plus b by 2, for any c lying between a and a plus b by 2, right? Okay, so what I'm writing is, so f, so how should I write? So f, let's say in this way, so f is integrable on c comma a plus b. So I have fixed one endpoint, okay? So a plus b by 2 for all c belonging to a comma a plus b by 2, right? This is by the function, because the function tells you that if you choose any 2 point in this ab, it has to be integrable. So now I know that this function is integrable on this interval, where c is just varying. A plus b by 2 I have fixed. Okay, now by a, okay, you can say that f is integrable on a comma a plus b by 2. This is by a, right? The first part tells you this, because this is something which is fixed. A plus b by 2 I am fixing. Okay, again, you can, by the assumption what you have, you can say that f is integrable on a plus b by 2 comma d for all d belonging to a plus b by 2 comma b, right? Again, by the same
Comma b.
what is wrong?
Nothing, sir, nothing.
Okay. So this is the assumption what we have, right? From the assumption we can say that f is integrable on this a plus b by 2 comma d. So I am using this fact. So d is here, a plus b. So in this interval it is integrable for any d. So this will tell you that f is integrable on a plus b by 2 comma b, and this is by b part, correct? Now I'll just add, this f is integrable on this interval and f is integrable on this interval, so it is integrable on this whole interval ab, and the integration you can write it as a to a plus b by 2 and a plus b by 2 to b. Okay, so maybe this, let's say 1, this 2, so 1 plus and 2 tells you that f is integrable on a comma b, and this abf, okay, is just a to a plus b by 2 plus a plus b by 2 to b. Okay, so this is how you can conclude the integrability of this function f on this whole interval ab. Okay, is this fine to everyone? Okay, if it's okay, then let's proceed to this last problem. Okay, so you have a continuous function f, okay, and it satisfies this kind of identity. So f at the point x, so what does this mean is that f at some point x is given by the, so maybe if you think this is the function f, then if you want to evaluate the function x, the function f at this point x, then this is given by the area under this curve, okay, till this point x. Okay, if such things happen and if f is given to be continuous, then you have to prove that the function is identically equal to 0. Okay, okay, so then let's try to prove it. So here we'll just use this identity, okay, this one, to get to the conclusion. Okay, so the first thing what you can note is that since the function f is continuous on this AB, so let me write, so it is bounded, right? So f is continuous on this compact interval AB, so it is bounded. That is, there exists M belonging to R such that mod of fx is less than equal to M. Let me write this in between. Okay, for all x belonging to A comma B. Okay, now let's use this identity. So you note that f of x is given by 0 to x f of t dt. Okay, now if I take the modulus, f of x is less than equal to 0 to x f of t dt, and this is less than equal to 0 to x mod of f t dt. Now you know that this function is bounded by M, so I can write this is M, right, times x. Okay, so here it was A, so it is x minus A. Good, so let's say this is 2. So this is another bound of f what we have got. So this was one bound, this is the another bound, right? We'll continue the same. So now, so here we have used 1, right? So using 1, so here by 1. If I use 2, okay, so maybe let's call this identity as star, okay, or something else. We call this as hash. Okay, so again, using the identity, using hash and this bound 2, we get, okay, so again if you repeat the same process, what you will get is, till here everything is same here. Now I will bound this by this quantity. Okay, so this would be A to x, and ft would be bounded by M times t minus A dt, right? This is the bound what I'll use, the second bound. So now I'll write this as M. If I integrate this t minus A, so I'll get t minus A square by 2 and A to x, right? And this is nothing but M x minus A square by 2. Okay, so let's say this, or so this is f of x is less than equal to M times x minus A square by 2. So let's say this is 3. If I again, now if I use 3, okay, then what I'll get, again I'll integrate this x minus A square, so I'll get x minus A cube upon 3. Repeat the same process, correct? So continuing in the same fashion, we have that this f of x is bounded by M times x minus A raised to the power n, okay, and then upon factorial n, because see, if you integrate again, you will get 2 times 3 in the next term, so that is the 3 factorial, so you'll get this kind of expression, okay, and this is true for all n. Okay, whatever n you want, you can reach there. Now my claim would be, maybe I can write it in different pen. So my claim over here is that this, okay, so again you can bound it further maybe. So this you can bound it as M times B minus A raised to the power n upon factorial n. This is true for all n in natural number. Okay, now my claim is that this term on the right, so limit n going to infinity, b minus a raised to the power n upon factorial n is 0. Okay, suppose I am able to prove it. Okay, now I'll prove although. So suppose this is true, then using this what I can say is this would imply that for large n, so this implies for epsilon greater than 0 there exist, so for any epsilon greater than 0 there exists a capital N epsilon such that this quantity b minus a raised to the power n, okay, upon this n factorial will be less than epsilon, right, this mod, or maybe less than epsilon by m. This I can do. So now if I substitute it here, what I get is, so this is true for all n, so in particular for capital N also it is true, right, for this n. So I can say that, so mod of fx which is less than equal to m times b minus a by capital N upon this n factorial, this is less than epsilon, right, and this epsilon is any epsilon, so whatever epsilon you choose this is going to be true. So this tells you that f x is equal to 0. So this was true for all x, right, so I should have mentioned, so this is for all x, right, everywhere I have not mentioned, but this is true for all x in AB. Okay, here also this is true for all x in AB. So this tells you that fx is 0 for all x in AB, right, since epsilon greater than 0 is arbitrary. Okay. Okay, so now the only thing what remains is that we have to prove the claim. Okay, so in proving the claim, like it's not a difficult task, but what you have to notice one thing is that this n factorial is becoming the growth of n factorial to infinity. So you see this term in the numerator also goes to infinity, the denominator also goes to infinity, but you see this n factorial, the rate at which it increases its value is at much higher pace. Okay, because this b minus is a fixed constant, right? So now if you keep on taking power of that fixed constant, okay, the growth by which it goes to infinity is slower than the denominator. Okay, so only we have to use that fact only to conclude that this limit is going to be 0. Okay, I think I have done this kind of problem in one of the sequences exercises, I guess so, but the same kind of argument I will try to use it here. Okay, it's nothing different. So the first thing what you can note is that, see, this b minus a, okay, this need not be a natural number. Okay, so just to compare it, okay, I'll try to write it in a form of natural number. Okay, so what I'll say is that there exists some k, okay, belonging to n, such that this b minus a is less than equal to k. Okay, then this b minus a raised to the power n by factorial n, this is greater than 0 by factorial n is less than equal to k raised to the power n by factorial n. Okay, so now my goal is to prove that this limit is 0. Okay. Okay, so now I'll try to, so if you notice, if I choose n to be sufficiently large, and in particular if I choose for n greater than equal to, let's say, k, I don't know if I need equal to k or not. Okay, anyway, let me write in this way then. So let's try to expand this one, k plus n factorial, okay, where n is a natural number. And how will this factorial look? So it is 1 times 2, 3, we'll get till k, then k plus 1, k plus 2, will go to k plus n factorial, sorry, k plus n. Okay, so now you see I'll just fix this as some constant. So this is nothing but k factorial. Okay, in this term, this k plus 1, I'll keep it as it is. Now you see this, how many terms are there? Here there are total k terms, right? And here there are total n terms, because 1 2 till n, this is 1 2 till k, so this is k terms and then now. Okay, so now what you can say, this k plus 2 is greater than equal to k plus 1, this k plus n is greater than equal to k plus 1. So every term I am bounding by k plus 1, so this is greater than equal to k plus 1 raised to the power n. Okay, then what you get is, so if I write this k plus n as, let's say, m, okay, so here my n was belonging from natural number. Okay, here I am using this change of variable, so what I can say is that for any m strictly greater than k, this m factorial is greater than equal to k factorial times okay, so this k plus 1 and this n, so suppose this is my m, okay, so m is equal to k plus n, then I will replace this n by m minus k, right? So this would be m minus k, and this is true for any m greater than k, correct? So this is what we have got. Now from here what you can write is okay, now what to do? So I have to reach this position, okay, k to the power n by factorial n. Okay, so let me do that. So for m, okay, so for m, okay, so sorry, yeah, so for m greater than k, if I try to look at this k raised to the power m by factorial m, okay, then I can bound this by just a second. Okay, so this is k by m, just a second. So I've reached at a good point. Okay, so now I'll use this bound. Okay, so now I have got this k by m. I know that this m factorial is bounded by this quantity, so I'll put it there, m factorial, and then I have got this k plus 1 raised to the power m minus k. Okay, so this is for m greater than k. Now you see this k by m, so now you can think this is
K
1
factorial, sir.
Oh, sorry.
If
This
you are
is k
going to
factorial.
substitute m,
Correct.
okay.
This is k factorial. So this is just a constant. Okay. So this is 1 by k factorial. This won't come in our evaluation. So this is 1 by k factorial. And then what you can write is, you can join this k and k plus 1. Okay. K plus 1. And then you write it as m minus k. And then you write k raised to the power. So what will the extra thing that will be remaining is k raised to the power k, right? It's just, yeah. So this is what you get. So I have got a bound of k raised to the power m by factorial m in this fashion. Now you notice that this term is less than 1, right? So if you take your m to be very large, so if you take limit m going to infinity, this is going to 0. So this term will go to 0 as m goes to infinity, right? So and this is anyway greater than 0. Okay, so by sandwich theorem, by squeeze theorem, what you have is that the limit m tending to infinity, uh, k raised to the power m by factorial m is equal to 0, right? So what you have, okay, so but m and n are same thing, okay, so there is nothing to worry. So what we have got is that this term goes to 0 as n goes to infinity. So then that's why again by Sandwich theorem, so maybe I should say this is star, or let's say how many I have used, 3, so let's say this is 4. So by 4, again by squeeze theorem, using squeeze theorem in 4, we get limit n going to infinity b minus a raised to the power n upon factorial n is equal to 0. Okay, so in this way you can prove that for any constant, if you take nth power upon factorial n, then that is going to be 0 as limit n goes to infinity. Okay, so this completes the proof of the claim and hence the proof of the result. Okay, is this clear? Okay. Okay, if it is so, then that's all for today. Okay, so there will be one more extra session so you'll get the mail. It's probably on this Saturday or Sunday. I don't remember the actual date. Maybe I can see. Okay, but whatever day you will get the mail, maybe there's a high chance that it should be on Sunday. I don't remember the date. So we'll have last session on that day, and so on that particular session we'll just try to solve one problem from each of the topic that we have discussed so far. So in this 12 week we have read many things, like, right? So sequences, then we got some series, then we got some continuous function, differentiability of function, integrability of function, then limit of some functions, right? So we have covered many of the topics. So I'll just try to pick one problem from each of the subsection, and then I'll try to solve each of them for you in that session. If you want some topic to be discussed on that day, you can tell me now, or maybe you can mail me as well. So if you want some particular topic to be discussed or to be focused more, if you even if you want to some theory to be discussed, I would discuss that. So it's all up to you, so how you want it to be done. Okay, so if you want some particular topic to be covered instead of going through each kind of problem, that is also fine to me, but you will have to tell beforehand. Okay, so if you are able to mail till tomorrow also, then that is okay. So maybe till tomorrow, if you are able to mail me, I'll try to cover those things, whatever you want. Otherwise, I'll just pick one problem from each of the topics and then I'll try to solve it. Okay. Okay, so is there some topic that comes to your mind that you want to be discussed in the next session? Okay, if not, then you have time till tomorrow. Okay, if you can do, that would be fine. Else we'll have this problem solving session as usual, where I'll discuss different kind of problem. Okay, kind of miscellaneous one. Mail ID I think I gave in the very first session, but still okay. So this is my email ID. Okay, you can mail me there. Mention just the topics that you want to be discussed, that I'll try to cover. Okay. Okay, then see you in the next session. Bye.